called the domain to another set called the range. For the mapping to be a function, then every element in the domain should be mapped to exactly one element in the range. So for example, we could name each of our birds, and that would be our domain, each of their names, and we could map each bird to the quantity of food that it ate. So the weight of amount of food would be an example range value. If the birds were tagged, we could map each bird's name. So again, the names of the birds would be the domain, to how far the bird flew from its home range. Or you could maybe map each bird to its lifespan. There are all kinds of mappings that you could do with any set into another set. In this video, we're going to focus on defining domain and range. On this screen, we have several examples of functions, and we will look at each one and discuss the domain and range. Notice in the upper left, we actually have two functions mapped on one graph. They are both for different compensations, one for a salesperson named Hal and one for a salesperson named Pia. So we're mapping sales, like various amounts of sales, to various amounts of pay. The graph below it is representing the record rainfall or the average monthly rainfall in a certain location according to months. So our domain is the set of months in a year, and the range values are amounts of rainfall in centimeters. So once again, on that graph, you have two different functions. One's represented by a red graph for record rainfall and the other for average monthly rainfall. Then we've got another example function where we're mapping a little set of turtles to their weights. So again, the domain would be the set of turtles, so their names, or if we numbered them, their numbers. And then we have two generic functions that are identified just by some formulas. And both of these functions happen to have domain, the set of all real numbers, and different ranges. So these are all examples of functions. Some are mappings where we're literally drawing arrows from turtles to values. Others have formulas attached to them. Some of them are maps of collected data. Just a reminder, you do not have to actually fit the definition of a function to have a meaningful mapping. So here we have an example in which we have three categories that would consist of our domain: at least 2,000 hits, at least 3,000 hits, at least 4,000 hits, and all of those domain elements are being mapped to more than one element in the range. The range are the baseball players, and there's really hundreds of baseball players that have had at least 2,000 hits. I have selected just a few that you could map at least 2,000 hits to. Same thing with at least 3,000 hits. Now, at least 4,000 hits, there's only been two Major League Baseball players, Pete Rose and Ty Cobb, but it is more than one. So this does not fit the definition of a function, yet it certainly is a mapping that provides information. We have another graph on here about median home sales in St. Louis, Missouri. And if I look at March 1st, for example, there are two different values mapped. March 1st is mapped to two different values. And without more information about the two different values, I'm not able to answer the question if somebody asked, what value is March 1st mapped to? It could be around 165,000, or it could be around 180,000. I would need more information in order to distinguish which one to answer. So again, that graph does not fit the definition of a function. You can easily see by kind of, looking vertically at any particular date, there is more than one value that the date is being mapped to. Then we have two other generic graphs. One is a hyperbola, the other is a circle. Again, there are many important astronomical elements and construction elements that are modeled by hyperbolas and circles. They are important graphs. They just don't fit the definition of a function because you have more than one point mapped to different x values. Let us discuss the domains and ranges of these various functions. In the upper left-hand corner, we have a graph that's representing two different functions. One is for the compensation or pay of a salesperson named Pia. Her domain, or the domain of that function, is her sales in dollars. And numerically, it's 0 and every number greater than 0. So x greater than or equal to 0. Now, in reality, if you were listing her sales, it's going to be rounded to the nearest dollar or nearest penny. It's not going to necessarily be every single real number, but most likely somebody is just going to simplify the concept to saying x greater than or equal to 0 when they're numerically listing what the domain is. The range are values greater than or equal to 10,000. You can see on the graph that her base pay must be 10,000, and she makes a minimum of 10,000 and makes more money depending on how much she sells. So the range would be her compensation in dollars. Y greater than or equal to 10,000 is the numerical representation. And once again, if you were listing her compensation, you'd probably round it, to the nearest penny. So every real number is not necessarily a range value, but in general, it would be simplified to that notation, y greater than or equal to 10,000. A very similar statement can be made for the blue graph, which is Hal's compensation. So the domain is again sales in dollars, numerically x greater than or equal to 0. And the range for Hal is y greater than or equal to 30,000. His base pay must start at 30,000, and then he gets paid commission. It looks like at 200,000 the formula changes, so there's a gap in his graph, but that doesn't change the domain. The domain would still be y greater than or equal to 30,000. The graph right below that, there are two different functions represented on that graph. So the red graph is representing a function in which the domain is the set of months of the year. So each month listed is really what our domain is. And the range looks like the lowest value is 6 centimeters, and then every measurement in between that and 17 centimeters is hit at some point in time. So our range is between 6 and 17 centimeters for the red graph. The black graph again has domain months of the year, and the range is between 4.5 centimeters and 10 centimeters. Those values are estimated off the graph because we don't really have the data, but the value of 4.5 is close enough that for our discussion, it would make sense to state that. Now notice May hit the maximum of 10, and a time near the end of June, beginning of July also hits 10. It's okay for two different domain values to be mapped to the same range value. So it's okay for May and July to both get mapped to 10 centimeters. It still is a function because May is mapped only to 1 and July is mapped only to 1, etc. In the upper right hand corner, we have our function that's mapping the turtles to the weights. So if you named the turtles, the 4 names would be the domain, and the range are their weights. And so the range literally is just that set of 4 numbers is the range for that example. Our last 2 examples are of generic functions. There's no application applied to them. In the middle, we have a parabola, 0.3 times the factor x minus 8 times the factor x plus 5. I can take any number I want and plug it in for x. So the domain is all real numbers. I will generally state all reals or just write an R to mean all real numbers. You could also express that idea by stating negative infinity, comma, infinity. and that would express the idea of all real numbers being your domain. I don't really care as long as you're accurately stating it's all real numbers when it is. You should be aware that writing negative infinity, comma, infinity is another way to express the idea of all real numbers. Now, it's not labeled that clearly on the graph, but that lowest point where the parabola is turning has a y value of negative 12.675. So the range is y greater than or equal to negative 12.675. Any number higher than that is reached by some x value being plugged in, and negative 12.675 is reached by plugging in the x value that's right in the middle where that vertex point is. The last graph is an exponential function. E, by the way, is kind of like pi. It's a special irrational number. It's approximately 2.718. So I have 550 multiplying e to the 0.4x. Once again, you can put 0, you can put negative values, you can put decimals, you can put positive values in for the x, and you will follow the calculation and get out a y value. So all real numbers is the domain. However, it is not possible for an exponential function to ever be 0 or negative. If I plug 0 in, e to the 0 is 1, and 1 times 550 is going to be 550. If I plug a negative value in for x, I will have e raised to a negative value, which is equivalent to 550 divided by e to some value. It'll become a very small value, but it will never actually be 0 and will never be negative. So the range is y greater than 0. Any positive number is reached by some value of x being plugged in, but you'll never hit 0 exactly, and you'll never hit any negative numbers. So again, the range is y greater than 0. Well, that covers a few examples. We are going to look at some more. In the upper left, we have the function y equals 50 over x minus 5. The domain is the set of all possible values that you are able to plug into the formula and get out a numerical value as an answer. So, for example, I can plug in 3. 50 divided by 3 minus 5 would be 50 divided by negative 2. That would be negative 25 as a numerical answer. I could plug in 0. 50 divided by 0 minus 5 would be 50 divided by negative 5, or negative 10 as a numerical answer. But if I try to plug in 5, I will end up with 50 divided by 0. And 50 divided by 0 is not a numerical answer. It creates the idea of going to negative infinity or positive infinity, and you can see that in the graph. If you look at the graph near x equals 5, on the left, the graph is soaring down to negative infinity. On the right, the graph is soaring up to positive infinity. So my domain is simply stated x is not equal to 5, and that means any other value except 5 can be plugged into the domain. The range is y not equal to 0 because every other value except 0 can be calculated by plugging in some x. You can see that you're not going to be able to get 0 because the function is a fraction, and fractions equal 0 where the numerator is 0. But what's in our numerator? 50, and it stays 50. It's never going to change from 50, so it will never be 0. Hence, the domain in this case is y not equal to 0. Any other value except 0 can be calculated as a range value. We have another rational function in the lower right, 50 divided by x squared minus 5, and this time we create 0 in the denominator by plugging the square root of 5 or negative square root of 5 in for x. if you square square root of 5 or you square negative square root of 5, you will get 5, and once again 5 minus 5 would be 0. So in this case, the domain is x not equal to the square root of 5 and x not equal to negative square root of 5, meaning any other value except those two can be plugged in. Now the range is a little more complicated than the last value. We can see once again that it's not possible to get 0 because the numerator is 50 and is never going to be 0, so 0 is definitely not in the range. But if you look at the graph, you can notice that the graph kind of hovers near 0 and then starts to soar to infinity near negative square root of 5. And then immediately to the right of that, there's this upside down U shape, and it's coming up from negative infinity and then turning around and going down back towards negative infinity. And then on the other side of square root of 5, we're coming down from infinity and then flattening out near 0, but never touching 0. So there's a gap in the possible values between the top of that middle U shape and the other two sections of the graph. It turns out, and if you look at the graph you can see this, that that U shape is turning around at y equals negative 10. So the range is from negative infinity up to and equal to negative 10. It actually does hit negative 10. And then there's a gap, so then we pick up on the other side of 0 and go up to infinity. So we actually hit negative 10, but it's not possible to hit 0. So notice the notation. Negative infinity is less than y is less than or equal to negative 10, union, meaning include, then from 0, less than y, less than infinity. The reason we hit that negative 10 is if you make the equation negative 10 equals 50 over x squared minus 5, you can solve that for x and you get x equals 0. So that's sort of the breaking point between getting a positive value and a negative value for the x squared. So it's possible to solve for 0 equal x squared, but not for a negative equal x squared. So again, if you want to see how we hit the negative 10, put negative 10 in for y, and then solve that equation, and you'll see, oh, I get x equals 0. All right, so again, one fairly simple rational function, one a little more complicated, but both are good examples. Here we have an example of a square root function. Rational functions give us restrictions, so do any even root. So a square root is an even root. And inside of our square root, we have 4x minus 1. If I put the number 1/4 in for x, 4 times 1/4 is 1, and 1 minus 1 is 0. The square root of 0 is 0. So this graph starts at x equals 1/4. And I get the square root of 0, which is 0. Any number larger than 1/4 will give me a positive value that I could then, figure out the square root for. But any number lower than 1/4 is going to make 4x minus 1 negative. And the square root of a negative value is not defined. So the domain is x greater than or equal to 1/4, and the range are all values greater than or equal to 0. So you could see from the graph that we hit the x-axis, so y equals 0 on the x-axis, and then we get values above the x-axis, so y is positive, but we don't get any values below that. So again, the domain is x greater than or equal to 1/4, the range y greater than or equal to 0. And we arrived at the 1/4 because that was again the breaking point between when the value of 4x minus 1 would be negative or when it would be positive. If you have any even root, so a 4th root or a 6th root or a 10th root, you need to define the domain as all values that would make what was plugged into it positive or 0. Both of these are examples in which I can plug any real numbers into the formulas. There's no restrictions. I also can get out any possible values. So the domain and the range are both all real numbers. Any odd polynomial is going to have that as the case. All real numbers can be plugged in. It's also possible to get out any real number. That is, plug any number in for x, you can do the calculation. Plug any number in for y, you can solve the equation. You can see from the graphs too that both of these graphs stretch out horizontally and stretch out vertically. So once again, domain, all real numbers, and range is also all real numbers. Here is another example with a parabola, and the domain is all real numbers. I can take any number I want and plug it in for the x and follow the arithmetic, and I will get out a numerical value for y. So the domain is all real numbers. But this graph comes up from negative infinity, it hits that point at the top, and then goes back down towards negative infinity. So the range is y is less than or equal to 14.5. The highest y value I hit is 14.5, and then I can get any value below that. I can't get any values above that. By the way, if you have a parabola and it is in this standard form where you have a number times x squared plus or minus a number times x plus a constant, that's standard form, you can find the vertex by following the guide that is on here. B is the number that is multiplying x to the first power. So we have -6 as our value of b. So again, you sometimes hear the standard form, ax squared plus bx plus c. So -6 is our value of b. Take the opposite of it. So take the opposite of -6, 6. Divide that by 2 times a. Our a was -2. So -6 divided by 2 times -2 is going to be +6/4, or 3/2. Plug that in for x into the formula. So if I take 3/2 and I plug it in for x, and I take -2 times 3/2 squared, and I subtract 6 times 3/2, and then I add 10, I get 14.5 for the y. So that's how I quickly found exactly what that top point was. I found it was 14.5 by following this little formula. Take -b times 2a, that gives you the x coordinate, plug it in, that gives you the y coordinate. So parabolas are always going to have restricted ranges. They have a point where they turn around. Here it's the maximum point, so all y values are less than or equal to 14.5. If the parabola opened upward, then they're going to have a minimum, and y will always be greater than or equal to some value. But the domain will always be all real numbers unless there's some application that makes restrictions. Here is an example in which the domain is all real numbers, so I can plug any number in because it's a polynomial. Polynomials will always have domain all real numbers. There are no restrictions. You can plug in negative, 0, positive, whatever. But if it's an even polynomial, there will be restrictions to the range. There will be a minimum or a maximum y value that gets reached. In this case, the minimum y value is 2. I can actually see pretty clearly from the formula that when 0 gets plugged in for the x, I get y equals 0 plus 2, and that's the lowest y value that I hit. I can get any y value higher than that by plugging in any other values for x. So domain, all real numbers, because it's a polynomial, but it's an even polynomial in the sense that the x is raised to an even power. So the range does have a restriction. In this case, the range has a minimum, y is greater than or equal to 2. I kept mentioning earlier that if you have an application or a word problem, it might create some restrictions on your domain and your range according to what the application is about. So for example, if we go back to Pia and Hal's compensation, it doesn't really make sense to say that their domain can go up to infinity, because during a year there probably is some limit to how much you can sell in terms of hoverboards and pickleball court kits. So just making up a number, let's suppose that it's never been the case that either one has ever sold more than $500,000 worth of their product. Then again, negative numbers do not make sense for the domain because you're not going to have negative sales. And so the domain would be any value of x between 0 and 500,000. Again, 500,000 is just, taking a stab at what might be a maximum amount of sales within a year. Once the domain is restricted, it does also restrict the range. So for example, for Pia's, she starts at $10,000 and her pay goes up according to what she sells. If she had her sales cut off at 500,000, then her maximum compensation looks like it's 85,000. Again, we don't have formulas to tell us exactly, but just looking at the graph, that's what it looks like. Hal's, on the other hand, if you restricted his domain from 0 to 500,000, his range looks like it goes from 30,000 to 70,000.